Hi everyone, welcome back. So we're going to talk about the C compiler in this video, the C compiler. And what we want to understand is have a better grasp at the process that occurs when going from a C program all the way down to an executable that can be loaded into your computer's memory, right? Loaded in memory for then the processor to execute. Okay, so there's these different steps along the way, and we've previously looked at a bit of an oversimplified view of this. So we're going to get a better understanding of how the compiler works, right? Goal of the class is to look at the hardware-software interface. We're going from looking at code itself, the code that you're used to writing in C, and going all the way down until it's ready to be in your computer's memory, and we'll look at the processor taking it from there later on in the course, right? So we're really seeing this whole flow from source code out till being executed on your computer's processor, okay? So this also, in addition to the kind of having good conceptual knowledge, to just understand how something works and how a computer works and some of the foundational knowledge, it is actually can be helpful to understand how to debug programs by understanding the different steps along the way and what parts might cause what types of errors. All right, so let's look at we're going to start at the top and work down. Okay, so let's look at a C program and kind of work down this kind of list here. So the compiler, typically when you're running a compiler, if you hit build or you run a compiler, by default, you actually run through multiple layers of this, like all the way down to the executable, right? But in reality, you actually there's multiple steps along the way of what's happening with the compiler. So a compiler is really, in its true sense, is just taking your C program and bringing it down to assembly language, okay? Now let's look at that first. So we're going to go from C program to assembly language, all right? So if we have a C program, we've got a C program. Let's look at what happens if we compile this in such a way. And we're going to tell the compiler to only go from the C program and stop here, not set to go by the default and just keep going and running through the assembler and the linker. All right, so we're just going to go this one layer. Okay, I'm going to do this example using the GCC open source compiler. Okay, I'm just going to use the GCC compiler, very, very popular, common compiler to use. Okay. And so let's take a look at this. I've got a program here. It's just a simple hello world program. That's all it's doing is printing hello world. Okay. And I'm going to, we've seen before running the compiler like this. All right, but I'm going to set a configuration, like a configuration flag here. The minus or -s tells the compiler to say, "Hey, only do that first layer." Right? Only go from here and stop right at the assembly language part. Right? Just don't go any further. So I'm setting that little configuration. I'm going to go ahead and run that. Okay. And when I go and look at what's in the, in this directory, I have some other files we're going to look at in a second, but it created this hello.s, file. That wasn't there before until after I ran the compile step. Okay. And if we look at the hello.s, all right, let's take a look at it. Okay, you notice that this is assembly language. Okay, this is not ARM assembly language. Okay? I'm using an x86 processor. It's an Intel processor. Okay, so this is a different assembly language. You'll notice that they actually, as you get some more experience, that they're incredibly similar. All right, there's an awful lot of similarities in terms of the fundamentals of how they work, right? And there's some things in here that we haven't seen yet that we're going to look at that's quite similar in ARM. But what effectively assembly language is, just to kind of recap what we're looking at here, is it's not ARM assembly, okay? But it is considered the as close to the underlying machine language that we can get with it still being human readable, that you can still actually code in it and look at it and make sense of it, right? If once it goes into all ones and zeros, our brains just don't work that way. Okay, so we're converted it into assembly language, right? The example I showed is in a different assembly language because we want to remember, right, that once we're at the C code, right, is independent of the hardware, right? Once you go into assembly language, that assembly language is dependent on the underlying hardware that you're running. Okay, it's machine dependent. Assembly language is machine dependent, right? If you go to a different machine, right, that has a different processor, different hardware architecture, supports a different instruction set, okay, the assembly language that will be generated from that C program is different. All right, so the compiler is transforming that C programming logic to something that is machine dependent. Okay. Once we've gotten at our assembly language program, the next step is we're going to run it through the assembler. Okay, the assembler takes the assembly language and runs it to the point of creating what is often referred to as an object, not to be confused with a Java object. Don't get confused with that in terms of object-oriented programming. It's a different concept, just a similar name just to make your life confusing. But it effectively is your machine language, right? It's taking that assembly language program, converting it to machine language. Okay, so let's go take a look at how we can do that. I'm going to run the compiler this time, and I'm going to run it in such a way that we go from the C program. It's going to go through the compiler to the assembly language step again, and it's going to continue running through the assembler, and it's going to stop here when it's created a machine language or an object. Okay, this module. So let's go ahead and do that. I can do that using the -C compiler flag. Okay, and when I do that, it created this object file. Notice the .o. Notice the .o. Okay, so I ran it, and again, with that compiler flag, it came from the C program down and stopped right here. Created this object file. Okay. Now we could look at that object file. We could look at it. I'm going to use a little strange technique to do it, where we're gonna look at it using, because we're going to look at it in hex, right? It is a binary file now. We're going to look at it in hex. So I'm going to come in here, right, and I'm going to open up the hex of that object file, and it's not really much to look at, right? Like I was saying before, when you're looking at machine language, I don't think anybody wants to code in this directly. Okay. Having a conceptual understanding of what it is, right? If you really want to truly understand how computers work, understanding the purpose of the file, what it's doing, what it's representing, but no one really wants to go in here and code directly in ones and zeros or hexadecimal, right? Okay, so what we've done at that point is we've kind of seen these different steps, right? We've ran through the assembler, we've got this object. Okay, now you might be thinking, well, aren't we done at that point? Okay. And as you can see from the diagram, we're not. Okay, we're not done because we actually have multiple. You have multiple object files, and let me tell you kind of why. Right, this is probably the easiest example to kind of represent it. Okay, let's say we've got our object file here. Okay, we've got our object file. Almost 100% of the time, you're using some sort of libraries, right? You're including libraries. You've got these different libraries that you're including. And, right, it makes sense. You want the libraries because it's code and functionality that other people have written that is really useful. You don't want to reinvent the wheel. You want to include it into your program. Okay? They need to be compiled in a machine language too, right? And it doesn't make sense to constantly recompile them. It's not needed to, right? Because they're used all the time. You're using them repeatedly. They can be compiled once, and they can be sitting as objects, right? Already compiled in the machine language and running through this step called the linker, which combines your machine language with the library. So effectively, your machine language code will have references to code that's in the libraries, but we need to combine them together into a single executable. Okay, a single executable. So let's do an example. Let's take a look at an example that's doing this. Okay, let's imagine here I've got this main.c file. Okay, this main.c file, and it's using a library, just to illustrate the example of including a library in this and linking them together. I created my own library. So I call the library mymathlib for my math library. And it's just, we're including it here. It's a very basic library. It's going to have two functions. If we look in the header file, right, this is the .h file. We just have these two functions, the power and the factorial function, right? Just purely for examples, right? We got these two functions included in the library. Remember from previous coursework, right? The header file includes the interface. It's the interface, right? Inputs, outputs, names of the functions. And then the .c file, the mymathlib.c file, includes the implementation, the logic that actually defines these functions. Okay. So we've got three files. The main calls everything is using the library. And what we're going to see is how we can kind of include these, like compile these together. Okay, we want to look at the linker. We're doing this in a way such we want to be able to look at the linker. Right, we want to look at this and understand how we can, for one, have two object files and then link them together. Okay, so we already saw how we can create object files. I can actually compile each one of those separately. Right, I can compile the main.c separately. Oops, I used the wrong. I can compile the main.c separately, and we saw that the compiler command for that was -c. Okay. If I look at that, it generated, I'm just doing the list this way with the asterisk.o, just lists only the .o files, the object files that have been created. And I just created this main.o, this main object file, right? I'm going to create one more. I'm going to do my math lib.c. Okay, now that one's there too. Okay. So what we have with these two, the main.o and the mymath.o, is we've done this part here. We've got this object file, and then the mymathlib is going to be our library machine language file. So you've got these two object files. Thing is, you can't execute the object files. You need to connect them together. You need to link them together into one executable. Right? And you remember, there's basically hooks between the two, right? This object file includes references into the library, basically function calls, but done at a level of ones and zeros. Okay. All right, so let's take a look at how we're going to do that. And we're going to use this -o. Well, I'm sorry. We can do. If I include the .o files, right, that will link together into, by default, it'll be a.out is the executable. This will know to link them together because they're object files, right? I could also give it a name. The -o will give it the name of the executable, whatever I want to call it. Math program or something. I could have also done that, right? Just to kind of remember from a prior video, if I say -o and then give a name, it will name the executable that. Just if I want to give it a descriptive name, okay? And then I can run that executable, which I named as the math program, okay? Whatever I want, just testing the power function and the factorial function, okay? So what we've seen, right, is again with the linker, I'm just going to be able to include the object files when I listing them out. There could be more than two, right? Using the GCC and just listing out the object files, it will then link them together. Okay, right. The end result is that executable, right? Now, one thing that could be kind of a handy thing to take a look at here is to take a look at the sizes of the object files versus the executable. Here's an example. I could show it in a moment with the real one that we just ran. But we were looking at the sizes of the files. And in this example here, there's two object files that were linked together. And then here was the final executable. And if you look at it, something doesn't seem right at first until you kind of think about why. Is if we add up the sizes of the two object files that were linked together, right? It should be around the 3000, you know, I think that's in bytes, right? 3000 bytes. And we look at that final, the final list there, it's about 9,000. And that seems like it's a lot bigger, right? Why would that make sense for to have such a dramatic difference in size? And the reason, if you thought about it for a bit, is because the system files, the system libraries are not included in this list up here, right? Your standard lib, your standard IO library, right? Those are also linked together when you create the final executable. So that's why, right? Just take a look here, right? If we take a look at the mymath object file, actually let's look at it this way so we can see it more cleanly. Okay, so here's the object files. We're going to ignore the hello one, right? So if we look down here, right, we see that the main object file is 2400. The math library is 1800, right? Now let's take a look at the executable here. We can actually see it up what I listed earlier on is about 8500. So notice there's a big difference between this 8500 versus down here, okay? And the reason there's such a big difference in size, when we look at the difference between these, is that this 8500 is also including all of these different system libraries that have been included in that number, right? So there's a whole bunch of additional functionality that's not included in these object files down here, these different system libraries that are also linked together, right? The way of thinking about that is here, I ran that, if we imagine this one being the main object, this one being the mymath lib object, you can imagine other system libraries in addition to that being linked in here, right? Because we included them in the top of the program, and they were compiled, or they were linked into the executable by default. So the sum of all of those would lead towards the actual byte size of the executable. Okay. Now we'll see later on. This is the last little step here. We're not going to get too detailed in it, but effectively there's an additional step in which that executable is actually loaded into your computer's memory, right? We will look at something later in the course where we start looking at the processor itself, and we will have something called instruction memory, which is effectively your program getting loaded into your computer's memory, right? It's in a position, so it's stored somewhere. That final executable is stored somewhere that we could then use it to process, right? To actually have the processor process it, okay? We will also learn some techniques on how to manage this compiling process in more detail, right? We will learn something called makefiles, which basically allows us to specify the rules of how we want to compile something, and we can define them once in one file, right? And then you don't have to memorize all the different ways of doing it. You can kind of specify how you want something to be compiled, and it will take care of the process for you once it's defined. It also has some efficiency gains if you're compiling something very large, but we'll look at that in a subsequent video. So thank you for watching. Sometimes I might intentionally go a little fast in the videos because I know you can stop and rewatch if something is confusing. It gives you that ability to do it. And we will follow up in class. So I will talk to you soon and see you in a future video.